So this is part of the testing series for input-output modules. So I have the module here, and it is meant to have maximum 80 milliampere output, about 4.6 volts output, and there's a polyfuse. You can see the golden colored component in the middle of the frame. So that part is when there's too large current, polyfuse heats up and expands and then develops more resistance, so that the current starts to drop, and when it cools down again, it resumes to the original state. So it kind of resets when it is let to cool down. It's been, let's see if this can focus. I have the thermal camera, but it's difficult to hold them both at the same time. So there's the power regulator and the choke, which is supposed to filter out disturbance. Then there's the polyfuse. Can barely see the temperature here, but it's a little bit over 100 degrees Celsius. And the regulator is 120 something. So it's been almost short circuited for a couple of minutes now, and it started at something like 300 something milliamps. The current is going through this 10 ohm resistor. So now it's 146 milliamps at 28 volts, which is more than I have rated these final devices for. So the regulator heats up much more than in the final devices, but I'm just testing it. So it is, if it's not continuous for a very long time, then the regulator does survive these 100 and something temperatures. It's not good for the board, but it can tolerate it, so I'm switching it off. Now it immediately starts to cool down. Let's see if this can focus again. It's very difficult to hold them. Yeah, now it cools down. There's the fuse. It's almost immediately cooling down. The regulator takes longer because it's much larger part, and the choke takes longest because it has lots of metal. So I'm letting it to cool down and then testing again. I can actually now, when it's almost, the fuse itself, it's very well cooled down. It's maybe 50 degrees, I think. I can touch it. The choke is very hot, but regulator is something like 70 maybe. Let's see. Yeah, 64. I'm switching on the power again, and this is maximum voltage. So you can see it went to almost 300 milliamps. And now you can see the fuse heats up, so temperature starts to low down pretty quickly, and you can see the fuse is glowing in thermal limits. almost immediately. So if I take off the lid so that it cooled down so quickly that I didn't even have time to grab the thermal camera. But it kind of protects the regulator against short circuit for long enough that you can sort out the issue. It is common with the small connectors that there's some issue with the leads and the different wires and pins, so there can be some small short circuit. I think I will test this by short circuiting it fully if I'm brave enough. This may be a bad idea with the power supply, but let's see. I'll take this. I want to film thermal image because this is interesting. I may ruin my table surface. Actually, let's see. I need to get some kind of stand. I also need one extra hand for this job, but yeah, kind of, yeah. Now switching it on and we can maybe see some smoke. This is fully short circuit. And the power regulator went over 100 degrees in a couple of seconds. Around 15, 17, almost 20. See, 120. But you can see, if I didn't have the polyfuse there, then what would happen? I would almost immediately burn the power regulator. So now it has, at least it should have something, maybe a couple of hours at least. If it stays under 130, then it could be days in that temperature. I'm not sure about the choke. It's very hot actually. That's the polyfuse. And we have 91 milliamps. It's not bad at all. It can survive this fully. 140. 38. Depends on the ventilation, but I need to check the regulator specs, but if you don't hold it in this state for very long, this would be totally fine. Actually short circuited fully. And you should notice it, because if you have a device which takes power from that connector, you will notice if it doesn't get any power. 100 degrees, something like that. Yeah, this is interesting. It's under 140. So yeah, now it's 140, but and inside the device it can well go to 160 something, but still, if you notice the short circuit quickly, then this shouldn't be a problem at all. If you happen to burn this module down, you can just change it. It has the quick connectors. It will be secured with 2 or 4 of those screws, but it's still very easy to change if needed. Yeah, now the fuse starts to expand more. Let's see. The fuse is very hot, over 100. Now you can see the regulator starts to cool down, so it takes a little bit for the fuse to heat up, but when it has heated up, then the regulator and choke start to cool down. The fuse is easier to change than the regulator and choke if you don't have a spare module, but you can actually repair this if you can solder the assembly parts. So 120, you can keep regulator like this in 110, 120 for days without breaking it. So yeah, the fuse works very nicely actually. So this is the input-output module for the 103, something like 14 for the fuse, 17 for the choke. The regulator starts to cool down. Yeah. Normally these modules are used at about 15 volts on the NPR or 20 something volts on the cp16R, so 28 is more than they are used at in normal conditions. So it doesn't heat us that much. Let's switch it off. It was 120 milliamps or something like that. Now and then I will lower the voltage to 21, which is more realistic for the cp16R. On again. Yeah. You can see the fuse is still hot because the current shouldn't go over something like 200 milliamps because the voltage is lower. But now it should see it up a little less. You can see the fuse is at something like 100. The regulator should heat less now because the voltage difference is smaller. And this is actually really good result. I can't see any smoke color difference here. Yeah, this is good result because I intentionally short circuited this output for long period and it just protects it just fine. So I can immediately destroy this device by short circuiting it. I could destroy it by having wrong polarity, but maybe not even. I don't think I could destroyed by wrong polarity actually, because it has these diodes with its isolated outputs. I could maybe destroy the optocoupler. Maybe. No, I don't even think so. Yeah, it's be pretty robust. It's easy to change this and it's expendable part, but I think it might be too difficult to destroy it actually. So, yeah, good result. Switching off the heat now. The fuse cools down so quickly that I can't even catch it here. Like 1 second or so. The regulator and choke, especially the choke, take a lot longer because it has this ferrite core and the outer shielding, so these take long to cool down. It's very hot. Regulator but fuse is almost, it's tiny bit warm, yeah. One issue with if you heat boards like this for extended period of time is for very high temperatures is that it can damage the structure of the board. This is 4-layer board, so, and it has, maybe you can see here, those small dots on the copper areas are vias. So it's a hole which is covered with copper layer and it goes through the different layers of the board and connects them together, different tracks on different layers. These vias go through all the 4 layers. So if you stress these boards for years, heating them up to 140 degrees and cooling them down and heating up again, then you can mechanically stress those vias and the component leads and so on, so you can have so tiny cracks and make the board unreliable in the end. But let's not short circuit this every day, hopefully. Or you can just buy new module, spare module if you manage to heat this up so badly that you manage to break it down. I love this polyfuse actually. It works beautifully. So it doesn't cut off the power, but it limits the heating to manage levels. Yeah, good result. I think this is about finished now. I may do some destructive ESD testing with this. So using a voltage generator running 500 or 1000 volts to the inputs and see if it comes through or not, but let's see. The copper isolator, this is really well working, but because it's 4-layer board, maybe you can see, maybe not. There's the middle section is the board base, and then on either side there is the top layer and then insulating layer. It is pretty thin, and then the second layer underneath it, then the board body, and on the other side there's the 2 layers with an insulating layer between. So if the static electricity discharge goes through the two layers on the same side of the board, there's less insulating material. And I needed to make this module pretty small, but still able to hand solder and repair the reflow issues by hand soldering if needed. So this needs to be curtain size, this module, so I couldn't get super high ESD shielding levels on this, but it's enough for this use, more than enough. Maybe 6-layer board would be better if needing something like 5000 volt or 2000 volt insulation, but that's not needed in this use. This should be totally fine. And I will make like 40 this summer, so this will be, even when hand assembled, this will be pretty cheap modules. So it's not the end of the world if you somehow manage to break this, because you can just have a new one, even if the original one cannot be repaired.